In the last video, we saw the definition of the pullback of sheaves. So if you have a morphism from X to Y and F is a sheaf on the target, then you can pull it back. And the abstract definition that did the trick was that you define this pre-image sheaf F and you tensor over the pre-image sheaf of OY with OX itself. And this gave us this pullback sheaf on X. And the definition, I mean, here there's lots of sheafifications going on in order to define this. But if you restrict to nice open subsets, namely if X is spec R and Y is spec S, and then F, the sheaf is actually quasi-coherent, so it's given by this M tilde for some module M over S, then you can define the pullback here equivalently as the quasi-coherent sheaf associated to the module M tensor over S with R. This becomes an R module, and so you get a sheaf here on X equals spec R. And this definition was a bit complicated, but in fact, whenever you do calculations, you will often just need some properties of this definition. And so in this video, we're collecting some of these nice properties. And we start with something very basic, the first kind of very basic example of pulling stuff back, namely, if you pull back just O of Y, the structure sheaf, then what you get by definition, we can actually just use this definition, you get here this sheaf of rings F inverse of OY tensor over itself with OX. And then in general, somehow in commutative algebra is true, is you have two rings, A, B, and then you take A tensor over itself with B, then this is always isomorphic to B. And then if you write this down, then you will see the pre-sheaf that you get here is already given by OX itself, because here's 2 times the same thing. And so pulling back OY just gives OX. And this is very good. So somehow this is one of the basic building blocks. Once you know this, then you can already start calculating a lot of pullbacks. Then next one, that's actually important if you don't just want to know about the sheaf, but actually about its sections. And so if you have such a map here, X to Y, and you have V inside Y, an open subset, and a section of F on that, then you get by this pullback also a section on the pullback sheaf of the pullback sheaf on the pre-image of V. And this is denoted by F star of phi. And this is what we would expect maybe from functions, right? If you have a regular function here, then pulling it back, you get a regular function on this pre-image. And the same, and somehow if you compare to A, if you set F equals to OY, then this is exactly what this here says, that if you have a section of OY on V, if you pull it back, you get the section of OX on F inverse of V. So this is the generalization of this. And to construct this and to prove that this works, well, we have seen that this F inverse of F is a sheafification of a certain pre-sheaf. And let me just denote this here by this pre-sheaf, whose values on an open set U inside X were given by these pairs of an open subset V containing the image of U and the section on there, and then up to an equivalence relation. So somehow if you take U equals F inverse of V, so this red part here, then of course this V is an open subset which contains the image. And so in fact this V comma phi that we input as the data here is a section of this pre-sheaf inverse thing on U. And we always know that the pre-sheaf maps to its own sheafification. So somehow this thing here maps to F inverse of V as we defined it. And if we have this section here, then we can map it. And then we get this thing inside this F inverse of V on U. So we are already kind of in the first tensor product here. And then we can define this pullback of phi under F as just take this thing here and tensor over over that ring with 1. 1 is an element of this OXU, the constant function. And then we are in this tensor product. So we are, a priori, we would be now in the pre-sheaf tensor product, right? If just taking the thing like this. But then this also maps to its sheafification, which is the definition of this sheaf. So somehow here in this example, just to write this down, we had to go through this entire construction again once, involving all these sheafifications. But in the end, nothing really happened. We just observed that somehow this V of F was already a section of the pre-image sheaf, and then if you tensor with one, you get this. And even though the construction is a bit involved, it satisfies some very nice properties. So, for example, one thing that you would maybe expect is that if you have a function on V, so you have now this section phi here and also a function, then of course you can multiply them because this F is an OY module. So then you have, I guess this is psi, so you have the function psi times phi here. And then you can first multiply and then pull back, or of course you could first pull both back separately, then you get a function and this section here, and then you can multiply them. And the statement here is that this gives the same thing. So if you pull back the product, then it's the same as first pulling back this. This gives a function. This gives a section of f star of curly f, and then you can multiply them like this. And here, this gives a bit of intuition why we have this strange tensor product going on. Namely, okay, let's try to write down this side here, right? By definition, this side is given by taking this V and then psi times phi tensor with 1. And somehow this psi here, now we observe this psi is in F inverse of OY of F inverse of V, right? Because psi, we just see it as a function on this on V, and so this gives an element here. But this is exactly this. We tensor here. This tensor product is over this sheaf of rings, and so somehow this allows us to pull this to the other side. This is exactly what tensor product says, right? If you have a vector coming from the ring over which you take the tensor product, then you can pull it to the other side. And so somehow if you do that, then you're left with this V phi, and then tensor with 1 times. And now if you pull it back to the other side, you need to use this map from F inverse of OY to OX. And this is exactly the image of psi under this map is exactly F star of psi. So here we use that the tensor product is over F inverse OY. And here, this thing is the image of psi under this map from F inverse OY to OX, because this map is basically F star. Okay. And so we have put this to the other side, but now here, well, 1 times this is just this itself, but then the final thing, we want to end up here. So we want to pull this out. So what we want to write here is that this is the same as F star psi times V phi tensor 1 again, because this expression here is exactly this. But this works. This is okay, because we defined the OX module structure on this F inverse F tensor F inverse OY with OX by multiplication. So if you want to do this product, you just take the product in the second term. So this is basically by definition. And then we started here with this side, which gave this. And we end with the right-hand side, which gives this. So this completes the proof. So this all seems like a bit of general nonsense, but here really we did use that we could pull out this term to the other side because the tensor product was exactly over the ring of all such functions of this form. So this works out. And so we do get a pullback of sections. And this has also some nice properties which with functoriality. So in particular, if you have the composition of two such morphisms here, and F is an OZ module, it's all the way here, then there's two operations you can do. You can first pull F back to Y and then to X, or you can pull it back all the way directly under the composition map. And the claim is that these two things give the same answer as OX modules. And the proof, let me just do the affine case here, because then it's actually very nice. You see what is the commutative algebra effect behind this. So assume that all the three schemes are affine. So there's spec R, spec S, spec T. And then this thing is comes from a T module. Then what do you get when you do the pullback in stages like this? Well, it's F star, and then we know the G star of the M tilde is just take M, tensor it over T with S, and then take the tilde. But then we apply the same recipe again. Doing F star of this means take this module. This is now an S module, so you can tensor over S with R, and then take the tilde. So this is just applying the recipe for pullback in the affine situation 2 times. But now you have kind of 2 tensor products, and then it's just a lemma from commutative algebra that just tensor over S, tensor over T with S, and then tensor over S with R. You can immediately tensor this thing over T with R. So somehow it's the same thing here. But this, by definition, is what you should do if you pull back all the way here via the map going from T to R, which defines the composition. So this is the definition. Sorry. This is the definition of G composed with F star of vertical. Okay. So the pullback is functorial. This comes just from this commutative algebra fact here. And yes, and so one particular class of morphisms for which the pullback is very easy and it gives exactly what we expect is if we pull back by an open embedding. Because then it just follows immediately from the definition that this pre-image sheaf of F is just F restricted to U. Just write down the definition. In fact, even before you take the so somehow, even if you just take the pre-image pre-sheaf, it's already F, and so F restricted to U, and then sheafifying this sheaf doesn't change anything. So the pre-image is very easy in this case, and then the pullback, well, then you just, by definition here, you take the pre-image sheaf, which is the restriction, tensor over also the pre-image sheaf of OX, which is also the restriction, and this gives just OU with OU. And while tensoring any OU module over OU with OU doesn't change anything, so we just get F restricted to U back. So pullbacks by open embeddings are just restrictions. And then an important concept which helps a bit to understand what this pullback actually does is that you can use it to define the fiber of a sheaf at a certain point. So let's say F is a sheaf on X and P is a closed point. So for example, if X is a scheme like this, and then you have the inclusion. And this is always a morphism like this. Yeah, I mean, I guess that here you should maybe, yeah, maybe if X is a variety, this is nicer than this is just the spectrum of field or whatever. But in any case, somehow just on the topological level, we can do this thing. So if you have this inclusion and you have a sheaf on F, then you can pull it back and get a sheaf on the single point set. But a sheaf on a single point set is not very interesting. I mean, somehow there's just two open subsets, right? There's the empty set and the one point set. The empty set must always have the value 0 for a sheaf. So the only interesting thing is what are the global sections? What are the sections on this full set? And so you just give this a name and you say that the fiber of F at this point is just, well, do this pullback sheaf and then evaluate it on the full set of this one point thing. And this is the fiber, and this is a, for example, if this was a sheaf of abelian groups, it's an abelian group. If this was an OX module, then this is I guess a vector space over the or somehow it's a module over the ring of functions on this OP. And if you actually have a factorization, so somehow if this P which maps to X, I mean this must have a neighborhood which is an affine variety because X is covered by these affine varieties. So we always find such a U which is spec R sitting in between. And then we can give these inclusions names. So somehow IU is the inclusion of U, and then this IP factors through this inclusion of the point inside U. And then we can actually use this functoriality which we just saw, namely, if we now want to compute the fiber of F at P, we can actually, instead of pulling back all the way here and then taking the sections, we can first pull back and then pull back again. So this is this part C, this functoriality like this. Then we can use that pulling back under this inclusion is just a restriction. So somehow this is just a restriction of F to U. And then if F is, I guess here we assume that F is a quasi-coherent sheaf, then this F is given by M tilde for some R module M. And now the good thing is somehow this this point here mapping to spec R, these are both now affine schemes. So basically you can see this as spec of R modulo P, modulo this prime ideal. And then if you do the pullback, you know what the recipe is in the affine case. You just take the tensor product over this ring, so over R, with this R modulo P. Where P is this maximal ideal associated to this point P inside U. And then F restricted, so somehow this fiber of F at the point P, the claim is then, well, this is just M modulo P times M on here. Because here, this tensor product we can actually perform. I mean, this is just a commutative algebra that if you take the tensor product over R with R modulo P, it just gives the modulo this ideal times the module. So this is just this thing here. And this then, in fact, is a vector space over the field of this point. This field of the point is just R modulo P. Since P was closed point, this curly P is a maximal ideal, so this is actually a field. And so when we have a section phi of F on some open subset which contains P, then well, we can first take the stalk of this section, or the value of this section in the stalk of F at P. And so somehow the stalk can be computed on this open neighborhood U. And then there it's just a localization of this module M at the point P. So we get this phi P inside this localization. And then if we take its image under this quotient map to this quotient here, then we get an element of, well, here we use this isomorphism that we saw here. Then we get an element of this fiber of F at the point P. And this we call the value of phi at the point P. So somehow the upshot is if you have a section, then we get the value of the section inside this fiber here. And maybe the interpretation, so why is it worth it digging through these definitions? So let's say you have now a nice situation. So F is a map between two varieties. F is quasi-coherent sheaf on Y on the target. Then we define this pullback. This gives us this sheaf on X. And then we can ask, what is the fiber of this sheaf at a given point P of X? And then we can again use this functoriality. So somehow you see we have P mapping to X. This here is X. This here is Y. This is the map F. And if we take these two compositions, then of course this map here is just the inclusion of the point F of P. So somehow P maps to here, maps to here. Then if you compose all the way, then it's just the inclusion of this image point. And then we can calculate this thing here. So somehow F star F at the point P. By definition, these are the global sections of pulling back under IP here. I guess here maybe one should take sections. But then we saw this pullback is functorial. So somehow instead of first pulling back like this and like this, we can take the pullback under this composition, which is just the inclusion of this point FP. But now we're in good shape because now we take the global sections of this pullback, and this is the definition of the fiber of F at the point small f of P. So this was a lot of talk, but in the end, what you just see is the fiber of the pullback sheaf at a point is just the fiber of the original sheaf at the image point. This is why this operation is called pullback. You just have the fiber sitting over here and you pull it back via this map, and then you transport it here, and then you have the fiber at this point P. And so what we're going to do next is to look at a useful class of quasi-coherent sheaves where all of these fibers are isomorphic at all of these points. You always get kind of the same, and they fit together nicely. And these will be the locally free sheaves.